Suppose a convergent infinite series converges to a sum S. If the nth partial sum Sn, so remember, we add up the first n terms, is used to estimate the sum of S, the truncation error. So truncation error, remember, is the error after, once you do a partial sum, you're cutting off the rest of the sums in the sequence. So truncating is cutting. So the truncation error is defined by our Rn, the absolute value of the error, so just taking it to be positive, is the true sum minus the nth partial sum. The alternating series estimation theorem. So suppose S is the sum from n equals 1 to infinity of sum minus 1 to the n minus 1, Bn. So this is some kind of alternating series. Now don't worry if you have a series that is minus 1 to the n, that's okay. So you can just think about that. If you just multiplied that series by minus 1, it would make that happen anyway. So suppose that is the sum of a convergent alternating series. So, and to be a convergent alternating series, well, you need to pass these tests. So then all the terms need to be positive. That's just the terms in the Bn part, not in the actual minus 1 bit, the bit that affects the sign. So all of those terms need to be positive, or not negative anyway. And the next term always needs to be less than the current term. So Bn plus 1 needs to be less than or equal to Bn for all positive integer n. And also, the limit as n approaches infinity of Bn equals 0. So those bits on the middle line there are just what needs to be, the criteria that needs to be met in order for an alternating series to converge anyway. So the truncation error, this is the theorem. The truncation error, which is the absolute value of the true sum minus the nth partial sum, is less than or equal to Bn plus 1. So this is a really, really useful result. So if you want to estimate to a given degree of accuracy, you can just find the term that makes this so, just by literally looking at terms. So here's an example of this. Find the sum of the series from n equals 1 to infinity of minus 1 to the power n minus 1 over n factorial. We need to find this correct to 3 decimal places. So the beginning would be to show that it's an alternating series, or show that it's a convergent alternating series. So if we think about this, we have the sum from n equals 1 to infinity of, and if I just pull the minus 1 to the n minus 1 bit out, so that's being multiplied by our Bn is going to be 1 over n factorial. So we need to show two things about this 1 over n factorial. Firstly, we need to show that it's always non-negative, and we need to show that 1 over n plus 1 factorial is always less than or equal to 1 over n factorial. That's the first bit. And we also need to show that the limit as n approaches infinity of 1 over n factorial equals 0. So it's quite clear that n plus 1 factorial is greater than n factorial for all positive integer n. In fact, factorials don't really make sense for any other type of n anyway, but we'll write it like this. So if we just take the reciprocals of these, we can say that, well, if n plus 1 factorial is bigger than n factorial, then 1 over n plus 1 factorial must be smaller than 1 over n factorial. We're dividing by more. And we know that everything's positive. Any factorial term will always be positive because it's just lots of positive numbers being multiplied together. So it's always going to be greater than 0 as well. So this shows that this is true. So Bn plus 1 is greater than or equal to 0, and it's less than or equal to Bn for all positive integers n. So the next stage is to try and show this. So the limit as n approaches infinity of 1 over n factorial. So it might be that we can compare this to something simple. So if you think about n factorial, well, if we have sort of values of n and values of n factorial, well, if n was 1, 2, 3, 4, and so on, we shouldn't have to go very far. 1 factorial is 1, 2 factorial is 2 times 1, which is 2. 3 factorial is 3 times 2 times 1, which is 6. 4 factorial is going to be 4 times 3 factorial. 4, 6 is 24. So that is going to keep going like that. I think 5 factorial is 120. So you can see that n factorial is greater than or equal to n for all positive integer n. So if we take reciprocals, 1 over n factorial must be less than or equal to 1 over n, and everything's positive. N factorial will always be positive for positive integer n. Well, it would be anyway, it wouldn't make sense for a negative number. And so everything is positive for all positive integer n. So that means that we can use a squeeze theorem to find this limit. Remember, if we were looking for to show series converge in this sort of style, that would be a comparison test. If you're trying to show a limit, then we use a squeeze theorem. So it's one of the first limits we deal with, the limit as n approaches infinity of 1 over n equals 0. Of course it does, as n approaches infinity, 1 over n must approach 0. Therefore, the limit as n approaches infinity of 1 over n factorial equals 0 also. And the reason is the squeeze theorem. It's not a comparison test, it's not a series. Okay, so that shows us that the lim as n approaches infinity of our Bn equals 0, and now we've met both criteria to say that this series is a convergent alternating series. So the sum from 1 to infinity of -1 to the n minus 1 over n factorial is a convergent alternating series. Therefore, the sum from n equals 1 to infinity of -1 to the power n minus 1 over n factorial is a convergent alternating series. And the reason for that is the alternating series test. Okay, so now we have shown that we have the sum of a convergent alternating series. We can then go into the actual question, which is asking us to solve this correct to 3 decimal places. Remember, if something's correct to 3 decimal places, then it means to be correct to the nearest 0.001. So if we want it correct to the nearest 0.001, then that means that Rn, the truncation error, remember the error when you cut off the rest of the series, needs to be less than or equal to half of that. So half of 0.001 is 0.0005. So we know from this alternating series estimation theorem that Rn is always less than or equal to Bn plus 1. Bn plus 1 is just a term in the sequence. I mean the sequence, not the series, as in the actual, in this case, the 1 over n factorial part. So if we can find the first term in that is less than or equal to 0.0005, then we know that we should be able to get this accurate to 3 decimal places. So we need to look at 1 over n factorial as a sequence and look at the terms. The easiest way to do this, remember it's a calculator paper, is to probably use table mode. So if we go to our calculators, I'm going to go menu table mode, and I'm going to type in 1 over divided by x factorial. So factorial can be found in the option part, probability x factorial. Okay, so we need to put some settings. So if we look from, remember we've got positive integer x that we're interested in. So let's look at the first 10 terms and hope that one of those is less than 0.0005, and if it isn't, then we'll just look at more terms. Okay, so there's the table. Okay, so we need Bn plus 1 to be less than or equal to 0.0005. So our calculators given everything in standard form. So let's write a few of these out so you can see there's certainly not, until you get to the standard form numbers, that they're obviously not smaller than it. So if we start with B5 equals, well that is 8.3 times 10 to the minus 3 is going to be 0.0083, so it's still bigger. Look at B6. B6 is 1.3 times 10 to the power minus 3, so that would be 0.0013, still bigger. And if we look at B7, well that now is times 10 to the power minus 4, so 1.9 times 10 to the minus 4 is going to be 4 zeros. 0.00019. So now if we compare down here, you can see that B7 is smaller than 0.0005. Bn plus 1, Bn plus 1 must equal B7, and Sn must equal S6. So what do we mean by that? So we now know that the absolute value of S minus S6 is less than or equal to B7. So the absolute value of S minus S6, remember S6 is the sum of the first 6 terms, is less than or equal to B7, the 7th term in the sequence part. So that means that S minus S6, just taking that absolute bit, well, it must be less than or equal to B7 or greater than or equal to minus B7. So that means that the true sum, S, if we just add S6 to everything, must be less than or equal to S6 plus B7 and greater than or equal to S6 minus B7. So now we need to add up the first 6 terms in the series, and we are going to have to use the series and not the sequence, so we need to make sure we get the signs right. So just make sure we know if the first term is positive or negative. So with minus 1 to the power n minus 1, so when n equals 1, it would be minus 1 to the 1 minus 1, minus 1 to the 0 would be 1. So it starts off being positive. So S6 minus B7. Remember, S6, first term is positive, so it's going to be 1 minus 1 over 2 factorial plus 1 over 3 factorial minus 1 over 4 factorial plus 1 over 5 factorial minus 1 over 6 factorial. And then we need to take away B7, which is 1 over 7 factorial. Okay, so S6 plus B7 plus B7, well, that is going to be, S6 will be exactly the same. So 1 minus a half plus 1 over 3 factorial minus 1 over 4 factorial plus 1 over 5 factorial minus 1 over 6 factorial. But this time we add B7 on, so that would be plus 1 over 7 factorial. Okay, so now we go to our calculators and we're going to have to use factorial, so I would just get it ready. It depends on which calculator you're using, really. So we have 1 minus 1 half plus 1 over 3 factorial minus 1 over 4 factorial plus 1 over 5 factorial minus 1 over 6 factorial, and in this case we take away 1 over 7 factorial. So that gives us an answer of 199 over 315. And for S6 plus B7, we just need to go back up to that and just change the sign of that last term, which gives us 177 over 280. Okay, so that means the true sum is less than or equal to, greater than or equal to. We need to, because this is a decimal question, we've been asked to correct to 3 decimal places, we need to turn these fractions into decimals. So 199 over 315 is 0.6317460,317, and 177 over 280 is 0.632 1428571. So all of that considered, remember the question, we have been asked to find the sum of the series correct to 3 decimal places. And if you look at this upper and lower bounds, you can see that to 3 decimal places, this would round to 0.632, and so would this. So S equals 0.632, correct to 3 dp.